Stop worrying about homework and start learning with confidence. This is Ask Learn. Complete help for every subject. Like, share, subscribe for daily learning videos.
Hello, my name is Margaret, and today I'm going to help you out with this problem. How a little bit how I like to approach problems is I it seems pretty straightforward, but I really like to take my time and look at what is the problem asking me, and what is the problem giving me, and then how can I relate the two together with an equation or some equations? And like I said, seems like a simple concept, but sometimes it helps to really be explicit in how you approach a problem like this. And then it helps you really grasp at more complicated problems, or helps you solve problems faster. And then that really helps. Whoops, sorry. That really can help um, with test taking further down the road. So, with that, let's take a look at what the problem is asking us really quick. And so it's asking in what energies in kilojoules per mole uh, are associated with falling wavelengths, and gives us one in infrared, uh, in ultraviolet light, and in X-rays. So let's take a second. So essentially, wavelength in various forms of meters. And so let's take a second to think about what equations do we know that can relate energy to meters. And we're just going to take a second and ignore moles for now, because typically we can add this back in later for almost every problem. And so the first equation that pops into my brain is this one, where E is equal to hc divided by lambda, where E is, and this is for a single photon of light. And so this is where E is energy. H is Planck's constant. C is the speed of light. And lambda is wavelength of light. And these two right here are constants. And the nice thing about constants is that if you Google them, typically, they will almost always, especially if you look on Wikipedia, they're almost always transferred into every single unit that you can imagine. Now, on a test, that's typically not the case. You're kind of just stuck with whichever ones your professor or teacher will give you. But almost always, they're not going to give you one that you can't unit convert relatively easily. So for this case, I went and looked up the Planck's constant that will suit us best for this problem. And so the Planck's constant in the units we want is 6.626 times 10 to the minus 34 in joules seconds. And the speed of light in the units we want is 2.998 times 10 to the 8 in meters per second. And so now that we have all of the pieces that we need, because the wavelength is being given to us in the problem, we have the the constants we need in the units that we want, and we now know what we need to solve for. We have our equation. We can move on to actually solving what we want. All right, so let's move on to the infrared light. So E is equal to 6.626 times 10 to the negative 34th joules seconds times 2.998 times 10 to the 8 meters per second. And all of that will be divided by our wavelength here, which is 1.55 times 10 to the minus 6 meters. Now, before we plug anything into our calculator, what we're going to do is we're going to do a quick unit check here to make sure everything cancels out in our favor. So here, the seconds are going to cancel out correctly. So seconds here in the numerator and seconds in the denominator. And then our meters are going to cancel out, right? This meter is in the denominator and this one's in the denominator, I'm sorry, or the numerator. And then that will leave us with just joules, which is exactly what we're looking for. Like I said, we're going to worry about moles in a minute. And so calculating this out now, this gives us 1.282 times 10 to the negative 19 joules per photon. Now, so because photons, because light is peculiar in the fact that it acts as both a wave and a particle, we can use Avogadro's number on photons. And so here, what we're going to do is we're going to take the conversion that we use way back towards the beginning of Gen Chem, where we use the number of where we use the classic 6.02 times 10 to the 23rd for things like particles and atoms in the number of moles in order to be able to get joules per mole. And so this cancels out photons and particles, and this ends up giving us 777,190 joules per mole for infrared light. Now, there's two problems with this answer. It's not that it's not fully correct, it's that we're not incorporating two things. The first one is that the number they gave us here at the beginning has only 3 significant digits, so we need to incorporate that here. And right now our answer is in only joules per mole, which they asked us to give it in kilojoules per mole. So we're going to do that conversion right now. Really quick, we're just going to move our decimal place over 1, 2, 3, put that there. And then we're going to leave off anything that's not 3 significant figures. And so we're going to chop off these 2 and we're going to round. So that'll give us 77.2 kilojoules per mole for our energy for infrared light. Okay. So let's move on to UV now that we have that. So we can use this exact same equation right here that we've come up with already, this nice box that we've figured out, and we can transfer it over here. So 6.626 times 10 to the negative 34 joules seconds, and 2.998 times 10 to the 8 meters per second. And I'm going to show you a quick trick right here in order to help you out a little bit. And that is how to use scientific notation to your advantage. So when you have something in place in front of a unit, like here we have nano. What that's really saying in comparison to our base unit meters here, is it's basically replacing times 10 to the negative 9 in front of meters. And so what you can do is you can basically substitute this in front of this 250 right here, and we can rewrite that as 250 times 10 to the minus 9 meters. Because we can't put nanometers inside our box over here because that doesn't cancel out with meters. And so if we just plop this in here, we'd get the problem wrong. But sometimes a full-on conversion takes a little extra time. And so this is something to just help you shortcut a little bit. And while this isn't necessarily proper scientific notation right here, the calculator doesn't necessarily care as long as you've put everything in with your parentheses properly. So what we're going to do is we're going to write in 250 times 10 to the minus 9 meters. Now the other correct way to write this is 2.50 times 10 to the minus 7 meters. That's the correct way to write this if you want. Okay. And so then our answer from there is 3.6183 times 10 to the minus 17. And once we tack on our Avogadro's number, we can then say that we have 4.78343 joules per mole. And again, we need to think about kilojoules and our number of sig figs. And so when you add those all together, what you end up getting is 478 kilojoules per mole. So this is energy of UV. So we'll move on to our final number, X-ray. Now we could still use the same trick that I taught you before here, but it also happens to be the correct way to write it in scientific notation. And so you have 5.49 times 10 to the negative 9 meters. And so when we replace that into our equation from before, we have 6.626 times 10 to the minus 34 joules seconds, and 2.998 times 10 to the 8 meters per second. And we have our wavelength, 5.49 times 10 to the minus 9 meters. And from there, we have 3.6183 times 10 to the minus 17 joules per photon. And we tack on Avogadro's number, 6.02 times 10 to the 23rd particles. And that gives us a very large number, 217.93329 joules per mole. Then once we add on sig figs and kilojoules, we get 21800 kilojoules per mole for X-ray energy. And so you can see as we go from just energy from the sun up to UV radiation from the sun, that's considered a lot more dangerous, all the way up to X-rays, we get an increasing amount of energy per unit. And I think that's really the takeaway from this problem here. And so I hope I was able to really help you today. And if you have any other questions, please let me know. Thank you.